Okay, so let's continue with an introduction to to this course. Sorry. Basically, if you think about it, we are surrounded by data. Okay, think for example the user ratings that you can check in so many websites online before watching a movie or deciding what movie to watch. Think of purchase histories. Okay, if you have ever bought online, you can check your previous purchases. You can check, the types of purchases that you've made. For example, the example that you see here is distributed by, grocery, fruits, dairy, or cheese. So you can see, how much money you've spent on different types of products. There's also document collections. So for example, when you read papers can be organized by different types of research areas. You've probably heard as well about genomics. So there's a whole branch of computer science that focuses on, the development of different methods to understand or identify patterns from genes and sort of kind of be able to associate specific gene patterns to specific illnesses. Neuroscience, similarly to genomics, okay, it's just another different type of data, which in this case are MRIs, imaging. And mostly images data that cover or represent a certain part of our body. And so, there's researchers and medical researchers that try to identify patterns associated to specific types of illnesses again. We might also think about social network data. If you, for example, visually represent how different people talk to each other, for example, this could be networks from Facebook or from Twitter, and you could see like different colors representing different types of individuals and show how different communities talk to each other, or the types of themes that are covered by different communities. So social network data could be another type of data that's out there. If you think about location-based services, the more famous one could be could be Foursquare. And so basically, every time you are at a place, you check into that place, and that's going to tell Foursquare that you are in that place at a specific day of the week and at a specific time. And so they can understand what your interests are. But globally, at a city scale, they can also understand hotspots, popular places, popular areas where people spend most of the time at different times of the day. Another type of data set that's been recently quite popular is also cell phone data that's collected on your cell phones, which could be GPS data or which could be CDR data, okay? So the location can be at the cellular tower level. So, every time you make a phone call, there's a cellular tower who's gonna give coverage to that phone call. And so location information for the cellular tower is collected. There's also other ways of collecting location information on your cell phone, for example, through mobile applications that you have installed. And so many or most of, mobile application companies will highly probably collect location data, even for, applications where in principle that wouldn't be necessary, like, for example, weather applications. And so, that GPS data or the CDR data, cellular tower data, can give us an understanding of, the most visited locations or the traveling patterns for different individuals. Financial data, okay, that's also like one of the oldest data sets out there. Basically, how do different values, change? For example, in this case, you see Dow Jones Composite Average, but you could be plotting, many other different, values or from many other different markets. And so as you can see, there's a plethora of different data sets out there, sort of more traditional data sets, but also new data sets that have been generated by different types of more novel, technologies, like, for example, cell phones or mobile applications, or, our access to different types of online platforms that allow us to do different things or different activities that we used to do them offline. Now we can do them online, but as a result, we're generating a lot of data. And so as you can imagine, that data can be used to answer many different types of questions, depending on the service and on how and why that data is collected. So for example, if you think about Netflix or about video in Amazon, and so on, and different platforms that allow you to watch, movies online or series online, the data from, the movies that you watch, what other people watch, and your demographic data is used to build up recommendations of, what other movies or what other series or what other products you might like. And so, for example, if we know that a given user like Transformers, okay, and we know what other people also like Transformers, and we can also check what movies these other people have watched. We should be able to recommend you a movie that highly probably you might also like. And so that's something that a lot of online companies do, again, with products, with movies, in which they basically look at demographic or socioeconomic characteristics of their customers. Okay, they look at all the titles that they have or all the products that they have, and they sort of try to recommend products based on individual and collective past experiences. And that's just one potential use of data that we generate. With the genes, as I mentioned earlier, they're heavily used in biomedical informatics. They are used to understand what are the sets of genes that might be associated to specific illnesses. Okay, and that's critically important. Like before, we had this type of algorithms. Nobody knew anything about the genes. Nobody knew anything about how genes were connected to different illnesses. Now we have these really large, really big data sets with genetic information from many individuals and from many different illnesses, and we can start to look for different patterns. In terms of, for example, social media data, how can we use that data? So there's a lot of work on, for example, understanding community dynamics, like how people talk to each other. Okay, and oftentimes the research questions that are answered might not be necessarily interesting for the platform itself, but they can be interesting because they replicate studies from the social sciences that were done offline in the past. Like, for example, how people talk to each other or how communities talk to each other is something that has been studied for many years, even before social media existed. Okay, and now a lot of those social science research questions are being moved towards online platforms and trying to understand how those interactions happen online. And so, community dynamics is something that has been studied also for a while. In this case, I'm showing, from a paper from 2005, I'm showing the political blogosphere. And so you can see, how Democrats and Republicans, are separated by color. And you can see how there's this sort of echo chamber where, they talk to, their own communities only. And there are very few interactions among them. Like if you look at the yellow circles, those yellow circles are the ones that basically talk with both Democrats and Republicans. Everybody else, as you can see, it's like these two very dense subnetworks, and they only talk to each other. And so this type of research has been used again to understand what brings communities together, to detect discourse polarization, to understand what people are talking about online, and so on. Other types of data that I mentioned before are images, okay? And so, for example, images, a lot of people, one of the most well-known platforms where people upload a lot of images is Facebook, for example, or Instagram. And as you can imagine, those platforms run a lot of various algorithms to try to identify who's who in those pictures and label them. And so, one potential application of that could be to pinpoint you to photos where your friends are, or to basically identify, your picture, identify where you might appear, in pictures that others have uploaded as well. Specifically this application, but also other types of data sets, as you can imagine, have a lot of ethical implications in the types of analysis that we can do. Okay, for example, with the location data, there was recently an article in the New York Times that talked about, different things that can be understood from GPS data, which are a lot. There's a lot of privacy concerns with the different types of information that we can that we can retrieve. And similarly with, for example, Facebook images, there might be people who actually don't want to be labeled or automatically tagged by the system on pictures that they have not uploaded themselves, but for example, friends have uploaded and they don't want to be tagged on those pictures. And so there's a lot of ethical issues that I will also talk about in a while in today's class. And so if we are surrounded by all these different types of data, and there are all these different questions that are being answered and so on, how can we define data science? What is exactly data science? And there's no consensus for this research question. Okay, so I'm just going to offer here my definition. You will find various other definitions, but I think that data science can be defined as the design of novel algorithms or the combination of existing approaches to extract information that is embedded in the data, mostly structure. Like what types of structures can we extract from the data that will pinpoint us to interesting findings or characteristics of that data. Oftentimes, the data sources that we use are generated by humans, right? For example, if we think about all the social media data, if we think about the cell phone data, okay? And so we will be talking about human behavioral structures, right? Rather than structures, for example, say in, medical images, which are generated by machines. We might also be looking into behavioral patterns, like how is it that people talk to each other online, or how is it that people move, for example. The data science pipeline has three critical components. The first one are the data sets. The second one are the features that we can extract from those data sets. And the third one is the task that we want to perform, the structure that we want to find, okay, the characteristics within that data set that we want to extract. And let me, for example, walk you through an example of what a typical data science pipeline could be. We can start with the data sets. For example, here, I'm showing you a data set that represents historical air quality data. Okay, so you have on the x-axis are the days, on the y-axis are different measures like PM10, NO2, SO2, which are different measures for air quality. And so imagine that we want to predict air quality. Okay, how could we predict it? So, we could just predict it with this time series, okay? Oftentimes, the way time series data is predicted is by looking at historical time series data and just looking at previous patterns and try and understand, or predict what could be the air quality data for the future. But we could also be looking at other data sets, right, that might also be predictive of air quality. So, for example, the reason why the air quality in a city is low could be due to the fact that, there's a lot of movement across the city, right? And that movement could be by car, but it could be by other things. And so we could use measures of human mobility. We could use information from roads. We could use information from different points of interest. So, for example, if we know that there's an area in the city where there are a lot of restaurants, that area is probably going to be very popular and very visited, as opposed to other areas. And so, if we have data sets with these other characteristics or these other features, we could also use those to predict the quality of the air. With the datasets that I have described, we could extract human mobility, like people moving from one place to another, and we could model those from GPS data. We could extract also how roads are used from, say, for example, taxi data. There's taxi datasets out there, for example, for New York City. We could extract points of interest, and all those could be features, variables that we extract from the datasets. And then we can use these features for a prediction problem. Okay, independently of what features we choose, they're always going to be either categorical or numeric. We can also describe them as discrete or continuous. Okay, either they take a set of values or they take a continuous numeric value. And then third component, we've seen that we need data sets. We've seen that we need to extract features from those data sets. The third component are the algorithms. Remember that we, in this case, the example that we put is that we need to predict the quality of the air using different features. In our case, We could predict the air quality based on previous values of the air quality, which is the temporally related feature. So basically, how was the air last week? How was the quality of the air in this same week, but 1 year ago? But we could also add other features, like for example, what I mentioned before, we could add taxi data features, mobility features, points of interest, and those could be sort of more spatial features, and add those to the model and see whether we can predict the air quality better or not. This example, I have extracted it from a paper from KDD in 2013. And what this paper interestingly showed is that if we only used air quality data as a time series to predict future air quality data, the prediction was good. But if we enhanced that prediction with features extracted from other datasets, like for example mobility patterns or points of interest, the prediction for quality was even better. So what this tells us is that it's extremely important to understand what datasets we want to use and what features can be extracted from those datasets, because the prediction can have the data that we use. And this is a more detailed representation of the data science pipeline, okay? But it's, again, same thing. So, we have data sets out there. We select some of those because we understand that, they might have interesting variables. Then we do some type of pre-processing and transform the data, and then apply various machine learning or data mining methods and interpret those results. As I mentioned earlier when I was talking about the use of images on Facebook, when we are using these data sets, there might be a lot of, ethical issues in using them, okay? It could be that, some of the data that we are using is highly private, and so we have to question how we are using that data and for what types of analysis, and whether the way we're using the data is different from the original purpose when the data was collected and that users were made aware of that the data was being collected. There might be ethical issues in the way the data is used, like for example some people, as I was saying before, might not be willing to be recognized on images on Facebook, on pictures that they have not uploaded themselves. It could be the datasets have biases, for example, in the data itself. Like you train a model, but that dataset has some type of biases. And so then your algorithm is just going to enhance those biases. And those are things that you have to be as well aware of when you use different models, right? There's this very well-known example about compass recidivism, and this is basically, a recidivism algorithm that some reporters tested, the algorithm that judges were using, so in a real setting, and they observed that there were some biases against certain groups, and so that certain social groups were being targeted more than others, or the implications were worse for certain social groups than others, okay? And the reason for that was just because the data had biases, because it had decisions made by judges, and so the model was picking on those biases and sort of enhancing them more, right? I really encourage you to read this algorithm. Overall, there is in data science a research area called Fairness, Accountability, and Transparency, or FAT. There's also a conference for this area. And although we are not going to go in depth into this, I really encourage you to think about the ethical implications about fairness, biases, and transparency of the methods that you apply for the research questions that you will pick for your semester-long project. And so, now that we understand better what's the data science pipeline, what are the different types of data sets, features, algorithms, what is it that we are going to learn in this course, which I guess that you are very interested in knowing about. So basically, we will learn three important things. First of all, how to collect and use different data sets to answer research questions. Secondly, how to extract features and understand what are the relevant features for our prediction setting. And third of all, how to use well-known algorithms to model or to predict behaviors, okay, but also brainstorm about potential fairness, accountability, and transparency implications, okay? And so by combining these three different elements, you will be able to work in data science problems from the very beginning, from, posing the research question and understanding the data sets that are available and what transformations we need to make to answer our research question, to, understanding features, feature selection, and putting in place the different predictive models that we need to answer the research question that we posed. The course is organized into sort of different components. Okay, so today's class is just, a general interaction. Class number 2 will focus on data structures and different packages in R. Okay, although I think that most of you are already familiar with R, I really want to cover that in one class and make sure that everybody, is at the same level. And also we're going to be seeing a little bit more in depth specific data structures that are going to be very useful for this course. Then I will also do a review of probabilistic learning, like, some approaches and some methods and very well-known techniques in probability that are fundamental to understand some of the more developed methods that we will see throughout this course. And then we're mostly going to focus on, again, as I was saying before, on predictive settings, mostly through supervised and unsupervised learning, okay? And then we'll also look a little bit into how we can improve these models by combining them into what we call ensembles, or basically, teams of models that work with each other to improve, the predictive, the predictive problem that we are trying to solve. And then throughout this course, through different examples, we will see applications of, different supervised and unsupervised methods to text, to social networks, and to as well as mobility patterns. Okay, so we will see how, the different methods that we are using can be applied in different settings. You will see that this course is highly applied. Every single method that will be introduced, you will see at least one example for those in R with one real data set. Okay, so again, the objective of this course is that you understand generally, what's the data science pipeline, that you learn how to carry it out, and that, after this course, you should be able to, join any data science group in industry and do, basic analysis in terms of supervised and unsupervised learning. I'd like to, briefly explain some of these components. So, for example, probabilistic learning, as I mentioned before, the reason why we are covering this is because some of the methods that we will see, like, for example, logistic regression, are fundamentally based on probabilistic methods, and I want to cover them so that, everybody is at the same stage. Also, very importantly, throughout this course, the methods that I will describe, I will not only describe, the package that you can use to run it, but I will also go in depth into the methods themselves, into the math behind the methods, okay? Always remember that now we are using R, but maybe, in a few years, we will not be using R, we'll be using other things. Now researchers are also using Python, right? And so, but maybe, in 20 years, we'll be using something different. And so the important thing for you to learn is not so much a specific package that you need to run, but rather, the math behind the methods. If you understand how the methods work, if you understand how the methods learn to predict, and if you understand all the parameters that those methods use, then it really won't matter what language you are using, okay? Because any language you will be able to use, okay? Because the important thing to be able to run this type of data science approaches is to understand how the methods work and what are the parameters. Once you know that, you'll be able to run them in any package, okay? On the contrary, if you just learn a specific package and you really don't understand what the parameters that you are manipulating are, then honestly, you won't have learned anything. Okay, again, important thing, make sure that when I cover the math behind the methods, when I cover the meaning of different parameters, you understand well what those parameters are and you understand what you are changing and manipulating. That's the whole objective of this course, okay? Again, I'm using R, but I could be using Python, I could be using any other language. The important thing is you understand the math behind and how those methods work. And that's the reason why we'll see some probabilistic learning as well. In terms of methods, we're going to cover supervised and unsupervised methods, okay? And the difference between the two is when we talk about supervised learning basically the algorithm, remember we have in the data science pipeline, we have data sets, features, and algorithms. And so the algorithm that we apply on the features that we have basically needs manually labeled data, right? So for example, imagine that you are trying to predict the length of a paper or the length of a leaf, okay? And you have different leaves from different types of trees, okay? So you need those leaves to be manually labeled to say what type of leaf is that, and also to have, the length of the leaf. A supervised setting, you need those manual labels to be in place. Your model will be trained taking into account features and manual labels, and your model will learn to output one of the manual labels based on the features that you have. Supervised learning generally is obviously much more stronger and robust than unsupervised learning, but on the other hand, it requires a lot of manual labeling, which oftentimes is not possible because manually labeling a dataset with 60 samples is fine, but manually labeling a dataset with 1 million samples is simply impossible. And that's the reason why we then have unsupervised learning. Unsupervised learning basically just takes what we call raw data, which is data that doesn't have any type of labels, just data that we have collected, and try to basically identify some type of patterns that we can then try to label. Okay, so if you think, for example, about the simplest, better well-known and supervised method, which would be k-means, clustering data points with k-means. The only thing that the algorithm does is to look for patterns or to look for points that are similar, and to put them in different clusters, right? And so what we can then do is manually observe, the data points in each cluster and try to sort of label them according to something, okay? In this case, the manual effort could be on the output and not so much on the data set that's inputted into the model. And then finally, as I mentioned before, we're going to be seeing different examples of applications using data from text, using data from social networks, that will also allow you to put in practice the methods, in extremely practical settings. Or, for example, not only social media, but also, for example, this is showing another example from a science paper that used cell phone data, the data that I mentioned before, basically based on cellular towers, location of how individuals move based on the location of the cellular towers that they used. And so, for example, this paper, they used this cell phone data and they showed that generally people, travel smaller distances and that they tended to spend most of the time in just two locations, which tend to be associated with home and work. Okay, and I'm going to stop here and then, we'll continue with the second part, which will be basically reopening our studio and then, looking into a few examples with our studio.